All right, everybody. So this is going to be a review of the Chapter 13 Universal Gravitation guided reading. Again, we are in Chapter 13 and we're starting off with 3.1, The Falling Apple. I'm just going to put it on my little presentation screen and we'll get started. So you had to describe the legend of Newton's discovery that gravity extends throughout the universe. And you should have something along the lines of this, that Newton got hit in the head with an apple and he came to the conclusion that they are both pulled by Earth's gravity. So not only is the moon pulled by Earth's gravity, but this apple is also pulled by Earth's gravity. And this is the idea that Newton came about with Newton's discovery of the gravity here. And so Newton understood the concept of inertia, and it was developed by Galileo that without an outside force, moving objects continue to move at a constant speed in a straight line. And this just comes from the Newton's first law, right? An object in motion wants to stay in motion, an object at rest wants to stay at rest until acted upon by a non-zero net force. Remember, if you have inertia, you have mass, so you want to continue in your motion, and you're going to continue in that straight line at a constant speed unless you are acted upon by a non-zero net force or some sort of outside force. So, true or false, circular motion is accelerated motion which requires force. This is true. So if we look at circular motion, or the motion of a circle, then we know that our velocity is always going to be the tangent line from where we are, or that 90-degree line from where we are, and that our acceleration is going to be pointing towards the center of mass, or the center of our circle. So in circular motion, accelerated motion, which requires force, this is true, absolutely. So Newton realized that the moon must be falling around Earth, okay? Not toward Earth, but around Earth. And we can see this in this cute little cartoon here where Earth is at the center and the moon is actually following this orbit that is causing it to fall around Earth. Okay, so again, acceleration is pointing towards the center of the Earth. Its velocity is going to be that tangent line from where it is now, that 90-degree line, if it was to follow in that straight line path. And this force is causing it to orbit. It's causing it to have this orbital pattern because it has mass, and it's being affected by this acceleration, and it has enough tangential velocity to carry on in this orbit or to fall around the Earth. So true or false, the moon falls beneath the straight line it would follow if no force acted upon it. This is true. So if you look at the little diagram that I provided to you on your worksheet, you're going to see that this moon is going to follow that tangent line if it weren't for the Earth there. And that Earth has a bigger mass, so it's going to cause a force of attraction between the moon and the Earth. And this force of attraction is going to cause it to orbit around. And the moon falls beneath the straight line it would follow. Yes, that is true. It falls right beneath that straight line if it would follow. If that moon was to carry on in a straight line for 1 second, that would be that red arrow line. And this green dashed line of orbit would be like 1.4 millimeters from where it should be. Okay, so again, acceleration is causing it to move towards the center of the Earth, or to accelerate. And remember, acceleration, that's a change in velocity over time. And we can change our velocity if we change our speed, or if we change our direction, or if we change our magnitude, or how fast we're going, and if we change our direction. So because we're changing our direction, we're actually accelerating. Okay, so this is true. So Newton compared motion of the moon to a cannonball fired from the top of a high mountain. And if the cannonball was fired with a small horizontal speed, if it was a small horizontal speed, then it's going to follow a parabolic path just directly to the ground, right? It's going to zoom off a little bit and then it's going to go directly into the ground. A faster horizontal speed, again, it's going to zoom down but have a longer parabolic path. And if it was fired at a fast enough speed, it would actually start to orbit around the Earth because it has enough tangential speed, and it has this acceleration pointing it towards the center, and it's just going to continue to fall around the Earth due to this force of gravitation. So true or false? Newton believed that the mass of the moon affects how it falls. This is false. Newton did not believe that the mass of the moon affects how it falls. So why doesn't the moon hit the Earth? And you should have some type of answer like this. Okay, so why doesn't the moon hit the Earth? The moon is actually falling toward the Earth, but it has a great enough tangential velocity to avoid hitting Earth. Okay, so the moon is actually falling towards the Earth or around the Earth, but it has a great enough tangential velocity to avoid hitting the Earth. Okay, so it has enough speed. If it was to go in that straight line, it has enough speed to avoid hitting the Earth. It's just going to continue in that orbit. So true or false, Newton's theory of gravity confirmed the Copernican theory of the solar system, and this is true. And that theory says that the sun is at the center of our solar system and that we all revolve around the sun, so that is true. Which sentence describes the motion of the planet if its tangential velocity were reduced to 0? This is C. It would crash into the sun. So the sun has a greater mass than whatever object that we are on in the solar system, so it has that great mass. So we would be very attracted to the sun. So if we stopped moving altogether, if we didn't have enough tangential velocity, or if we was reduced to 0, just like it says here, then we would actually be gravitationally attracted to the sun, and then we would crash into the sun. True or false, Isaac Newton discovered gravity. This is false. He discovered the ideas of gravity, but he didn't have a name for it, and he didn't have the gravitational attraction constant, and by that I mean the universal constant for gravitation. So what is Newton's law of universal gravitation? So you should have, again, an idea that says something like this. So for a pair of objects, each object attracts the other with a force that is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. So if we increase the mass of our objects, then we are going to increase the force. If we decrease the distance of our objects, making them closer together, then we're going to increase force. If we increase the distance of our objects, then we're going to decrease the force. So it's all about this idea of gravity, mass, and distance and how they all relate together. Okay? So what is the equation for universal gravitation? Well, it says that F is equal to G, which is a gravitational universal constant, times m1 times m2, which is the masses of our objects, divided by the distance that separates them squared, okay, or this inverse square of the distance. So the constant G in this equation is called the universal gravitational constant, and it describes the strength of gravity. Okay, so how strong is gravity between these objects? And it's a constant, no matter if you are two marbles next to each other or to the Earth and the Sun, right? G is always going to be a constant between those two masses. And it's equal to 6.67 times 10 to the negative 11th Newton meters squared over kilograms squared. So this is our constant G, and it describes the strength of gravity. So the English physicist, let's get his name, Lord Henry Cavendish, was the first to measure G, and he built this contraption that was like a leveling device, and he said that, you know, G, or gravity, has to be equal to my force. Okay, so again, he set up this level and he set up masses on one side and then a large mass at the bottom, and he measured that distance, and then he put weights on the other side to get the force that was required to level out this beam, and then he solved for G. So he plugged in the mass and multiplied that together, divided it by the distance squared, and then divided it by the force that was needed to keep these things level, and he discovered G. All right, he discovered G to be 6.67 times 10 to the negative 11th Newton meters squared over kilograms squared. So true or false, the force of gravity is strongest of the presently known four fundamental forces, and this is false. It's actually a pretty weak force like we saw in class today with the magnets. So true or false, at the top of the mountain, your weight is slightly less than at ground level, and this is true because as you increase the distance from your center, then you are going to decrease the force that you feel. So if you decrease the force that you feel on your body, then your weight is going to be different. So what is the inverse square law? So I saw a bunch of different answers for this, but I just want to make sure that we have this answer down as it stands. So if one quantity is multiplied by a factor, another quantity decreases by the square of that factor. So like force and distance. So if we increase the distance, we're going to see a decrease in our force. If we increase that distance, then if we increase the distance, then we're going to see a decrease in the force. If we decrease the distance, then we're going to see an increase in the force. So what is the inverse square of 9? So basically what this is saying is that we need to take 1 over 9 squared. That's what the inverse square is really saying to us. So 1 over 9 squared is going to be 1 over 81. So that's what you should get for your answer there. If the mass of an object doubles, so if the mass of your object doubles, then the force is going to be multiplied by 2. So remember that mass is directly proportional to force. So if you double your mass, you're going to double your force. If the mass of an object decreased by half, so again, we're decreasing the mass in this scenario, so the force is going to be divided by 2. So we started out with an original amount of force, and then we decreased the mass of our objects to half, so we're going to have half of our force, or it's going to be divided by 2. So if the distance between the object's center of mass doubles, so if we're increasing the distance that we feel, we're going to have a decrease in the force, and the force is going to be divided by 4. So if you work this out, you're going to solve that you're going to get for 1/2 of the force that you would originally have. If the distance between the object's center of mass decreases by half, so if we decrease by half this distance, right, then our force is going to be multiplied by 4. And I would like to show you this. So we have F is equal to, let me pause. All right, so I want to show you this one out. So we have force is equal to G m1 m2 over d squared. So G is a constant, so it actually doesn't depend on anything in this case, because if we're changing mass and we're changing distance, then G is always going to be the same number. So I'm just going to cancel it out like it doesn't matter, but it does matter. But just remember, in this kind of case, it really doesn't matter. All right, so we have force. All right, our masses is staying the same, so I'm just going to put in 1 for our masses. And our distance is decreasing by half. So if I have a half here, I'm going to square this half, then I'm actually going to end up with 1 over 1/4. So 1 over this fraction, or 1 over 0.25, if you put that into your calculator, you're going to get a force of 4. So if we decrease our distance that we're going to feel, or we decrease by 1/2, then we are going to increase our force by 4. And so remember, it changes differently. It changes with an opposite proportionality, or this inverse square proportionality. Okay, so if we decrease the distance, then we're going to increase the force. All right, so true or false, gravitational influence of every object is exerted through space. This is true. So gravitational influence of every object is exerted through space, and this is true because we have this force. We have this force of gravitation that depends on G, depends on 2 masses, and it depends on the distance between them. So if we're thinking about Earth and the Sun, well, those would be our 2 masses. So we find the masses of the Sun, we find the masses of Earth, and then we find the distance between the Sun's center of mass and the Earth's center of mass, and then we use G, this gravitational universal constant. Okay, and it just tells us how strong gravity is. Okay, again, it's 6.67 times 10 to the negative 11th Newton meters squared over kilograms squared. So it's really, really small. So it really depends on our masses, and those are going to be huge, and the distance between is also going to be huge. So it is going to be this kind of large gravitational influence, but it's all over everywhere. Okay, it's not just on Earth. It's everywhere. It's what keeps everything in line and orbiting around each other. We have enough tangential velocity that if we were to continue in the straight line, we would. And then we have this acceleration that is causing us to move towards the center of our circle. And so we're going to keep in this orbit until we lose speed or until we gain speed. And then we're going to move basically towards the center of the sun. We'll see how that goes. All right, so I hope this was helpful. Let me know if you have any questions. See you all soon.